Um, Good morning, everyone. I'm Anurag, and today I'm going to be talking about our effort towards AI-powered computer systems at the edge, which will be through in-network resource management for disaggregated edge data centers. Let's dive right into it and see what the resource disaggregation actually is. So if you look at traditional warehouse scale data centers that are typically employed by cloud providers like Google, Microsoft, they're typically comprised of building blocks called servers, which we are all familiar with. And these servers are comprised of compute, memory, and storage units, right? And these warehouse data centers will employ tens of thousands to even millions of servers connected by a network fabric, right? Now, while these warehouse data centers can employ economies of scale by multiplexing multiple tenants with over these data center networks and these data centers, in edge data centers, we have much smaller scales, typically at the scale of a rack. So we want mechanisms that can provide much more cost efficiency at smaller scales of economy, right? And so one of the technologies that is really promising in this space is resource disaggregation. At a high level, what resource disaggregation does is it takes all the resources inside a server and decouples them. So essentially, you break apart the server abstraction and create compute blades, memory blades, and storage blades, all connected by the network fabric, right? So there is no server as such. And your entire disaggregated pool of resources serves as a computer. And this kind of an architectural change promises a lot of interesting new benefits, which is particularly advantageous for edge data centers. For instance, you get transparent resource scaling. You can scale each resource independent of the other and make sure that the amount of resources you have is just sufficient to handle the workloads that you are serving. You get high resource utilization by multiplexing each pool of resources across multiple applications independently to get even better resource utilization. And you can support hardware heterogeneity for supporting accelerators. It's particularly important for AI workloads that we are kind of targeting in the Athena project. And there are a number of other advantages as well that I won't go into the details of. But one thing I do want to note is that disaggregation is a radical architectural change, right? If you look at some of the target applications of the Athena project, they've been designed and optimized to run on traditional architectures, server-based architectures, and deploying them on disaggregated architectures would require redeveloping them or modifying them significantly to work on these new architectures, right? So the big research question, or the primary research question that we're asking in this project or in this particular subthrust is, how can we make these benefits transparently available to applications? And the obvious answer, which has traditionally been the answer for most such questions, is to provide an operating system support that abstracts the hardware and applications underneath, right? And the operating system would also be responsible for providing a host of other functionalities and responsibilities, such as resource elasticity by multiplexing the architecture's hardware resources across different applications, providing protection so that different applications don't mess with each other, and ensuring performance for the application so that they can get close to, if not equal to, the performance of the raw hardware underneath. And our approach to realize this vision for disaggregated operating systems, or an operating system for disaggregated architectures, is to place the operating system in the network fabric itself, right? And this is a sort of a strange choice or a drastically new choice compared to prior approaches. And so there are a number of driving factors that make it a very attractive choice for, particularly for edge data centers. First, the network is centrally positioned in the edge data center, right? And this provides two main advantages. First, by placing the resource access metadata and logic in the network path, you can actually perform the resource access logic within the data path of the communication without performing any additional round trip. So it kind of facilitates low latency and high throughput access to the different resources in your network, right? And The central positioning in the control path allows resource management mechanisms to actually leverage the global view of all resource communications, as well as the state of all the resources in the system for near optimal allocation and scheduling policies, right? And the other driving factor that has made it feasible and actually realizable today is the emergence of programmable networks, which can facilitate line rate performance for resource access and resource access logic with very low latencies. And another observation that we exploit is there are many similarities between the way operating systems perform resource management and the way network performance management, right? So SDN and the technologies that have developed in the last decade or so to come up and manage networks share a lot of similarities with how operating systems manage the resources. And our key insight is that we can leverage the decades of hardware innovation that has happened to make it much more efficient in the networking world to actually facilitate resource management much more efficiently for our edge data center. And we've already made some key headways towards realizing this vision. And the first step that we've actually taken is designing this system called Mind, which is essentially a memory management unit for this disaggregated data center. And this is already in collaboration with two of our Athena members, Lynn and Abhishek. And the high-level observation that we're exploiting in this project is essentially that in a disaggregated setting, the network is no longer just a general purpose communication fabric, but actually a compute memory interconnect, right? So we should leverage it as such. And what we do in this particular project is place the memory management unit, or the MMU, in the network. So all of the functionalities traditionally performed by the MMU, such as cache coherence, memory protection, and address translation, are now performed by the network switch in that setting. And this allows for a very efficient realization of memory management functionalities within the network itself. All right, so looking ahead, there is a lot more to be done to realize this vision. And I'm going to categorize them in the context of the Athena project in two main subthrusts. The first subthrust is the systems for AI thrust, where we design systems that facilitate AI workloads efficiently in the edge data center. And the high-level goal is to provide transparent support for AI accelerators via a network-centric operating system for AI workloads. And the second subthrust is essentially AI for systems, where essentially we want to leverage the AI technologies that our amazing colleagues on the AI side of things are developing and leverage them to perform much more smarter allocation of resources and resource management policies. So let me briefly go into the details of each of these subthrusts. In the systems for AI thrust, this is again in collaboration with Lynn and Abhishek, and hopefully some of our wonderful colleagues in the AI thrust. Our OS prototype and can already support some AI and machine learning platforms like TensorFlow. So we have been able to deploy TensorFlow and run them in our disaggregated prototype. But the drawback of our current prototype is that we can only support CPU plates. So essentially, we don't support any accelerators like GPUs or TPUs that are popular for executing AI workloads. And so embracing accelerators for AI or ML will require operating system support, right? And so there are very interesting research questions to be answered in this space so that we can actually support accelerators efficiently, including what is the right threading model that can actually transparently adapt any heterogeneous compute unit. So for instance, you could write a program for your CPUs and tomorrow I could just deploy it in your GPUs or TPUs based on whatever is the most optimal for that particular workload. And how do we reconcile different memory consistency models across accelerators when you're sharing memory across them? And this is particularly challenging because each of the new accelerator technologies that come up are built with their own memory consistency model. So if you want to share state or share memory across different accelerators and traditional compute units like CPUs, you have to reconcile the memory consistency model somehow so that the different entities can talk to each other without violating correctness properties. So the second subthrust is AI for systems. And this is again in collaboration with Lynn and hopefully some of our fantastic AI collaborators. The main observation in our setting is that even though network seems like a wonderful place to put all of the management logic and functionality, the network is particularly constrained in terms of resources because it is a central point and B, because today's programmable switches have very limited amount of resources and few megabytes of memory and compute units, right? So the question is, how do we share these constrained resources across different applications? And what we found is that traditional resource allocations can actually lead to high resource contention within the network, and we want somehow to resolve this. And so the key research questions in this space is, can we leverage the global view of all inter-resource communications in the network to enable more powerful AI-based technologies for resource management? And can you even predict future resource requirements and reallocate them to minimize performance overheads? So that's all I have in terms of slides. Thank you so much.